Alrighty, so we're going to start today talking about acceleration. This was one of our favorite cartoons a while back when the kids were young. Colin, you get your better, please. Okay, so what is the name of the Grinch's dog? I'll let you know, but don't say it out loud. I just like that, I like that picture. And I sometimes put pictures on the front page because then I know which one which set of notes I'm looking for, and I can find it easy. He's missing his big red nose and his antler. Yay, everyone got it right. Yes, it's Max. Buster was my dog. Wow, that. Now the little helper, of course, is Simpson, right? The reason that I have thought of this is because in that cartoon, when Max is sliding down the hill, there's that scene where he's sliding down the hill like the reindeer in front, and the Grinch is in behind, right? And the Grinch is going so fast that he overtakes the dog. You know that? And I'm thinking, how can the acceleration? This is what I'm thinking, right? We're watching it. How can the acceleration of the Grinch be greater than the acceleration of the dog? Talia. I can't help it. Yeah, gravity. Does gravity affect heavier things more?
No, because according to what's
Interesting, right? Yeah. So that's why I bring that up. Okay, so let's begin. So, acceleration, whoopsie, apparently, do I have to start the next one, or do I have to do this? There we go, okay. So, acceleration is, like velocity, is it a vector or is it a scalar? So A or B? Well, you just enter it. And make a decision. Is that something you need to write down? What is the definition of a vector? It has to have a direction. So do you think acceleration has a direction? Does it make sense to say like 4.6 meters per second squared east? Does that make sense? The question is, A, it is a vector. Acceleration is a vector. In fact, when we first introduced vectors, I said the big four are displacement, velocity, acceleration, and force. So acceleration is a vector quantity, which means when I ask you for the acceleration, you should also include a direction. So it can be positive, which means, don't say it out loud. Positive acceleration could be to the I'll change your name there, Brian. I can't do it while it's going, but I'll change it out. Just gotta press enter. Press enter. There you go. It is B and C.
You can't do three.
Yes, you can.
It doesn't let you mark B and C.
It says B and C right there.
But you can't. But you see damage.
Yes, you can.
You should have told us.
Yeah, you're cheating.
Once again,
That's like sticking you in a test.
do these marks count for anything?
Well, it does on that screen. It shows your body. Yeah, no,
You know what they do to me?
sure got at least 50%. Yeah. I got 0.
All right, well, can you get this one?
No.
Acceleration can also be negative, which is so acceleration can be negative, which is to the left or down. Now that's just arbitrary. That's just defined that way. We could change it if we wanted, but that's kind of what that means. Now this one here. It is a yes or no. You'll see Y and N on buttons number 1 and 2, I believe. So does deceleration always mean slowing down?
1 and 2.
1 and 2, is it A? I don't know.
What?
T and F.
I very rarely use the clickers, like myself.
1 and 2.
You'll see a Y and an N, and there's a T and an F as well, right? So does deceleration always mean slowing down? And this is really just a question to start a conversation. So don't get excited if you get it, quote, wrong.
You get it wrong, you get it wrong. Yeah.
I say no.
Why?
Okay, so is that something important, do you think?
Yes.
How do you know? Because I said that it's important?
It's in bold.
Yeah. Acceleration to the left, sometimes called deceleration, but be careful, it does not always mean slowing down. Now, in the real world, yes, deceleration means slowing down, okay? And in fact, in science and physics, I try not to even use the word deceleration, okay? Because, what if the thing is, wait a second here. So acceleration to the left, sometimes called deceleration, not in physics terms. So I'm just sort of alerting you to the fact that deceleration is kind of a word that's used out there, but in the world of physics, we try not to use that. Because if something's accelerating to the left, does that mean it's slowing down? Because what if it's already going to the left, and the acceleration is to the left? What if the velocity is negative? What if the velocity is -5 and the acceleration is -2? Well, then it's going to actually be speeding up, right? What do you mean? I'm not saying any time. I'm just saying moving. What? You can't move to the left. Things can move to the left, right? I'm not talking about going back in time here. So all I'm saying is that negative acceleration. That's really what I'm saying. Negative acceleration does not necessarily mean slowing down. Negative acceleration does not necessarily mean slowing down. Negative acceleration does not necessarily mean slowing down. Absolutely, you could. PDFs there every night. Yeah. Negative acceleration does not necessarily mean slowing down. Did you figure out, like, there was 2 or 3 of you that figured out what I wanted, right, at the start, right? How did I give you that cue? Well, I repeated it, but I said a little bit louder, and did you see what I was doing with my hands, too? I was emphasizing.
Saying you're going to hit us if you're right.
Exactly. Learn this, or I'm going to hit my other hand. Okay, so acceleration is the time rate of change of velocity. It is a change in velocity. Acceleration is a change in the velocity, the rate of that change. Acceleration is the time rate of change of velocity. Now I'm going to reword that. I'm going to put that in English terms. Try to give it in a language that you can understand. So I'm going to say how fast an object's velocity is changing. Acceleration is how fast an object's velocity is changing. There must be a change in velocity. There must be a change in velocity. And it's how fast that velocity changes. What kind of vehicles can accelerate? Colin, put that away, please. Listen now. What kind of vehicles can change their velocity very quickly? Why do you say Jeeps? Okay? Race cars, motorbikes, right? Motorbikes can go from 0 to really fast, really quick. Right? What kind of vehicles cannot accelerate very quickly? Trucks, buses, right? Jeeps. Exactly. It's how fast is an object's velocity increasing or decreasing. So it could also be speeding up or slowing down. Now it could also be a change in direction. Because velocity is a scalar, right? How fast is an object's velocity increasing or decreasing? Oh, I never spotted that one. Actually, you didn't spot the missing apostrophe here either. How fast is an object's velocity increasing or decreasing? Again, the emphasis on change in velocity. And I'm saying this over and over again because I know what's coming. I know the common mistakes that people make. Here it is another way. How fast you get to how fast or slow you're going. How fast you get to top speed. How fast you get to how fast you are going. It is not how fast you're going. Think about fighter planes. Okay? How fast do just planes in general, how fast do planes go?
Pretty fast.
Yeah, but they go pretty fast, right? But if you were in a plane and I had my 2003 Ford Explorer out on the runway, side by side with a plane, who would get up to 60 kilometers an hour faster? Me and my little truck. But a plane's going to go a whole lot faster at the end. That's true. Depends on the wind speed. Yeah, but depends how fast the wind they're flying into the wind too, right? Yeah. True enough. Okay. So now, based on what you know, I hope you guys are listening, because this is you've got to be paying attention. If you want to truly understand acceleration, you really got to pay attention. So, you might know this from grade 10 already. You might have been able to figure it out based on what I've said, because I've said that acceleration is the rate at which velocity changes. So, what is the equation for acceleration? Is it delta d over t, delta t? Is it d bar? Do you guys know what d bar would be? What does the bar mean? Average over time? Or is it v bar over delta t? Or is it delta v over delta t? That's what you would have done? Okay, did we get it right? The correct formula for velocity is delta v over delta t. Now, many of you are going to get this written on your test. At least I believe so. I hope you prove me wrong. Oops. No, it's not going to be the frowning face. Well, it might be. Hang on, I'm having a hard time writing it. V bar, is it equal to delta V? No, they are not the same. V bar stands for average velocity, and delta V stands for change in velocity. Average and change are not the same thing. The only thing that's the same is the letter V. I don't care, they're not the same. That's the Greek letter delta, the triangle. Yeah. Okay? So do not assume that V bar, don't just write V. That's why I do this. Don't just write A equals V over T. That's not right. It's delta V over delta T. Acceleration is a change in velocity over a change in time. Change in velocity over a change in time. Acceleration is a change in velocity over a change in time. And if I had to give you an ultimate sort of definition, that'll be it. Change in velocity. I keep emphasizing that. Okay, now, the sheet that I handed to you, if you're following along, if all you've done is just had the sheet, what I suggest you do is you can cut that out at home and tape it into your notes. You can just say, label it, see figure one. You can write right on the sheet. I don't care what you do. That's the graph I'm talking about, right? You've got it right in front of you there. So if you want to label it figure one or whatever, you do what you need to do. In the graph below, the displacement graph is a curved line, meaning that velocity is, don't say it out loud, EJ. This graph here, this displacement graph, position time graph, right? Just like the ball one in the lab that we did, this position time graph is a curved line, meaning that the velocity is decreasing, increasing, or staying the same. That's not an option apparently, but it should be. Decreasing, increasing, or staying the same. Again, this is a position time graph. A, B, or C. Correct answer? Yes. Increasing. The velocity is increasing, right? How come? The slope is changing. In fact, the slope is also doing what? Increasing. The slope is increasing. The steepness. Did you get that kind of graph in part 2 of your lab from the other day? By the way, you're going to get time tomorrow to finish that. Okay. Now, since the velocity is increasing at a constant rate, the velocity graph that corresponds to this, okay? This is the same one that you just saw. This is a position time graph. These are all velocity time graphs. Which one of these matches this one? Which one of these velocity time graphs matches this one? There is not. Your options are A, B, and C. This is the position time graph. Which velocity time graph, and this might be the first time you've ever seen a velocity time graph. It's a graph of the velocities. Which one of these matches? Velocity is the slope of the position time graph. The answer is B. Now, Colin, can you just say that? You were explaining it to Kat. Do you want to just explain that a bit loud? No? I do. I do, because I think I overheard you. I don't think you're entirely right, but I think right? You should pay attention to that. He's explaining. That's right. You're absolutely right. So like what you're saying is if I've got like a tangent right there, that's my slope, right? Yeah. But that doesn't mean that matches that. You're right, it did, but that's just by coincidence, right? The correct answer is, okay, if you found the slope at all those points, what kind of numbers would you get? Like, what would be the slope here at the start? It might be like 2 or something other. I don't know. I'm just making stuff up. That's a 2. We'll call that a slope of 3, and we'll call that a slope of 4. Right, Terry? You're not watching. How can you say yeah? This is the slope of 2. This is the slope of 3. This is the slope of 4. So if I graph the slope, then the values are 2 and 3 and 4. The velocity time graph is a graph of the slope of the position time graph. The velocity time graph is a graph of the slope of the position time graph. I think that's so important, I'm gonna do this. The VT graph is a graph of the VT graph is a graph of the VT graph is a graph of the slope of the PT graph. So, I'm going to ask you a challenge question here because I think you're the class to do it. What would the position time graph have to be like for the velocity time graph to be flat like that? Work backwards. What would the position time graph have to look like for that to be the velocity time graph? Diagonal?
Would have to start at a certain point and not stay.
Isabel, you're trying to be straight? Yeah? Like this? What's the slope here? The velocity is?
It's a constant slope, yeah.
Constant slope. Well done. And so you would get whatever the slope here is, right? Like let's say the slope here, I'm going to write m for slope. The slope is, say, I don't know, 4. What would this be right here? 4. Flat. It would remain at 4, wouldn't it? What would you have to have for a position time graph here to make it do that? This is a tough one. What position time graph would you need to make the velocity time graph look like that?
Would have to slow it, like,
Here the velocity, I like to say, is approaching 0.
you have to like position the car stop. It's not a rabbit.
What would the P graph look like? Here the slope is, like we'll say, like, I don't know, 5. And it goes 5, 4, 3, 2, 1, right? So how would the shape be? Show me with your finger.
It would look like a rabbit.
Like this, do you think, Riley?
I knew it.
Yeah, would it be like that? Let me think here. You're really close.
It would be
Why would it be the other way, Riley? What's the value? This here is positive 5. So when I drew it this way, oops. When I drew it, no, what's going on? When I drew it that way, what's the slope right here? It's actually negative, right? So instead of being that way, it would actually be, it would be like this, right? Because here the value is positive 5, the slope here is 5, and approaches 0. You're going to have to know this eventually. This is your first practice. Yeah, it's hard. Physics is hard. Okay, now, the acceleration graph is a graph of the slope of the velocity time graph. The acceleration graph is a graph of the slope of the VT graph. What was our VT graph? The original one that we had over here was this one right here. The acceleration graph is a graph of the slope of the velocity time graph. So you take the slope of the VT graph over many points and you graph that. Well, the slope at all these individual points would remain what? The same. Right? The same. The slope here is the same as the slope here, is the same as the slope here, is the same as the slope here, is the same as the slope here. And so the acceleration time graph is in fact flat. Okay? So if I said that the slope of this graph was 0.4, are you guys listening? Because this is hard stuff. You can't tune out. If I said the slope here is 0.4, then that means my acceleration graph here is at 0.4, and it remains 0.4.
This means that the acceleration is a constant point form. And this is known as uniformly accelerated motion. Uniformly means the same, and accelerated means there's a change. So we are speeding up at a constant rate. We are speeding up at a constant rate. I'll pause for a second. I'll let that soak in. How many people taking pre-calculus math? Excellent. So that means you're likely taking calculus at some point, because that's what pre-calculus means, right? Okay, so what I just taught you was the very, very basic intro to calculus. Okay? So you've got displacement, and then that becomes velocity, and then when you take the slope of that, that becomes acceleration. And every time you do that, every time you take the slope, you are taking what's known in calculus terms, you're taking the derivative. I'm always waiting for someone to say it. Usually I have to coach it. Well done. There is a slope and acceleration time graph, and that is known as, the letter is J, because it stands for jerk. It does. Because if something doesn't accelerate, like if you're in a car, right, and the driver puts their foot on the gas, you smoothly accelerate up to speed, right? It's really smooth, right? Maybe if Colin's driving, and he's already admitted to it, right? Exactly. How does it feel in the car when Colin's driving? It feels jerky. It's not because Colin's a jerk. My apologies, Colin. I know you're not a jerk. Right? It's that jerky, right? When the acceleration is not constant, then there's that jerk. Okay? And is there another one? Yeah, there is. I don't know the name of it. You can go derivative like as many times down as you want. Okay? I don't know what it's not. Okay, easy. Don't be a jerk. All right, way more advanced than you need to be. Okay. So, I've given you a lot to think about. Here's a question, a thinker. You have this graph as well, I think, right? You have it on that page, right? So this velocity time graph is an example of variable acceleration. What do I mean by variable acceleration? Variable acceleration, well, is it not constant, constant, or, well, it could be constant or it could not. I don't know. This is a velocity time graph. And acceleration is the slope of the VT graph. So is this not constant or constant? It is.
I'm gonna need more. Oh, sorry.
Colin, come on, man. Well, it's A, B, or C. Correct answer is, half and half. But what is the correct answer? A. It is not constant. Variable acceleration. What does variable mean? Variable means changing. Variable, more than one, changing, right? So it is not constant. Not constant acceleration. This is the velocity time graph. Now the next question is even harder, I would say. Do you want me to, are you writing something down there?
Yeah.
Sure. What could you do? On your little sheet there where you see that graph, you could write variable acceleration, not constant. You could write that down there. Okay. This is a straightforward yes or no. Does this object ever move backwards? No, not backwards in time, like just back, like forwards. Backwards. Does this object ever move backwards? Yes, it is a velocity time graph. That's correct, it does not. Well, not entirely true, but to you it doesn't. To me it does, but
We need like another graph.
you need to know how to read it. You'll know in about a week and a half. Yeah. Does this object ever move backwards? And I see lots of people talking about it, so that's good. That's what I want you to do. Does it ever move backwards? Riley says this is where the J comes in. Well done, you guys. The answer is no. Well, yeah, 50-50, right? Okay, can you explain what is happening between A and B?
It's slowing down.
Slowing down. This is a graph of the velocity. Does the velocity ever go below 0? Does it ever become negative? No. Negative velocity means moving to the left. All that's happening here is it's speeding up, and then it's slowing down, and then it's speeding up. So it's like, right? Just like that, but constantly positive. I practice that. I'm not going to hit the wall. Okay, my learned, wise friends. Draw me a velocity time graph with a similar shape, but just showing the object moving backwards. Instead of moving to the right, wherever you want. Wherever. Wherever. Sorry, you know what? Let me. I'm trying to remember what I really want you to do here. I want you to draw a simple shape. What would it have to look like? Same kind of shape. Same kind of shape, but you move backwards at some point. What would it look like if you actually did go backwards? I'll just go back to this one so you can see it here. What would it look like if you did end up going backwards? What would it look like? You can draw it right on that one, I guess, if you want, right? What would it have to look like to end up going backwards? Danielle's got it. For it to go backwards, it would have to do what? Right? Here, it would be backwards, right? So what it would do is it would be like speeding up, slowing down backwards, speeding up, and then this way, right? You want me to run into the wall. You're so mean. You're the slope of the acceleration time graph, Pat. Physics insults. Okay. Notice that the slope, I'm going to wrap up real quick. I think I'm close to done. You guys have been pretty good. Notice that the slope of the curve is not always positive, right? What is the slope right here? The average. It's negative, right? It's negative there. What do I have right here? So between points A and B, hang with me, you guys. We're just almost done. Okay, I know. How do you guys get through like an hour show on TV? No? Oh, I'm trying. Didn't you see me dancing up front? Notice between points A and B, what is delta V? Change in velocity. It goes from 4 down to 2, right? Watch, ladies. Hang in here. So it's 2 minus 4. The change in velocity is minus 2. How much does the time change? It goes from 4 to 7, so it's going to be, so A equals delta V over delta T. 2 minus 4 is my change in velocity. My time change is 7 minus 4, and I get minus 2/3 or minus 0.67 meters per second squared. The acceleration for that interval is minus 0.67. Does that slope calculation make sense?
Yeah.
Yes? Are you just saying that about it?
Yeah. I mean, no.
Karen? Are you just saying that, or do you understand what's going on? Because I need you to understand, right? Yeah, well, we'll be doing lots of practice, right? Okay. One last thing, and then I'm going to show you a video. One last thing. Notice the units on the acceleration. They are meters per second squared. Now, I'm just going to explain where this comes from. You don't need to write this down. All you need to know, Danielle, please, is that the units for acceleration are meters per second squared. This is why. Acceleration is the rate of change of the velocity, which is the rate of change of displacement. So in other words, don't write this down, just watch. A, acceleration, you don't need to write that down. Oh. All you need to know is that the units for acceleration are meters per second squared. That's all you need to know. A is delta V over delta T, but the delta V, the change in velocity, is made up of what? Karen, you still need to watch though. You have to. You have to. You can watch. You have, your attention span has to increase. It has to. You're going to have to work on it. Okay, and that's why one reason why we're here. The change in velocity is delta D over delta T, right? So now I've got delta D over T over T. Okay? Just watch. Acceleration is change in velocity over change in time, but change in velocity is D over T, right? So you see that I have seconds and seconds there. So using units, now don't freak out. Everyone always freaks out when I show this. Please don't freak out. Yeah, oh, you're just saying that. Okay, so what are the units? Distance is meters, time is seconds, time is seconds. So we have, using units, seriously, Taryn, meters per second, or meters per second divided by seconds. Now, how do you divide fractions? We've got meters per second divided by seconds over 1, or just seconds. How do you divide fractions? First you have to flip the second one. So instead of seconds over 1, we're going to have 1 over seconds. So meters per second times 1 over seconds. And how do you multiply fractions? You multiply straight across. Meters times 1 is meters, and seconds times seconds is meters per second squared. And that, my friends, is why the units. Colin, you were just away. You need to listen, not check your Twitter feed. Listen. And also point out that getting gum is not really a good reason to leave class. Your units for acceleration are meters per second squared. Okay? Meters per second squared. Okay. So this guy here, I'm going to show you the video right away. Galileo was the first scientist to clearly understand the concept of acceleration. He found that the acceleration of a ball rolling down an inclined plane or a ramp and the acceleration of a falling object were both described by the same mathematical rules. He was interested in falling objects, but he realized that it was happening too fast, and so he realized, and I wish we had one more ramp. Oh, I actually put it away, right? That if the ramp was like this, it rolls down, right? Well, what's to say, like, what if the ramp is like 89 degrees? Well, it's almost straight down, right? What if it's 89.9, right? So the rules are the same for straight falling as they are for rolling. And when it rolls down the ramp, then it happens slow, and you can observe it. So he built himself a really long ramp, made it very smooth to reduce friction. And here's a little video about it. Now, I probably will have to go and log in and all that. So now's a good time to just take a little mental break, and then we'll come back in about 30 seconds, and we'll watch it.